Alright, so structure we're going to look at is this one here with a 6-membered ring with a double bond connecting it to a ketone like this. And I'll just call that an OR group. That can be whatever because this is a very general sort of a disconnection, right? So we have an alpha beta double bond next to a ketone. There's the alpha carbon, beta. So when we see this, this is a very typical sort of retrosynthesis problem we'd get. So the simplest way to disconnect this is to imagine that this structure came from the dehydration of an alcohol group here. So maybe at the side here I'll just outline how that could happen. So if we had an alcohol group here, double bond O or alcohol, if we acidify that, or if we added an acid, we could protonate that and have a H2O plus, which would act as a leaving group facilitated by that proton leaving, giving you the double bond. So that is how we would end up over there. So basically what that means is this structure can come from this structure. That's all I'm saying. Alcohol there. Okay, so the next step is how do we end up with this alcohol in the 1, 2, 3 or 1, 3 relationship between a ketone and an alcohol. This is another really typical retrosynthesis problem. It's one of the simplest carbon-carbon bond forming situations. So when you see this, you need to recognize that the 1,3 relationship with oxygens can be disconnected by an aldol reaction. Aldol. Okay, so this is a condensation basically between a ketone and another ketone, or 2 carbonyls. So the first thing we need to do is we need to have this carbonyl and we need to deprotonate it. So let's assume there's a load of steric bulk here and this is really big over here. So if we want to just deprotonate this side, what we need to use is a hindered base such as lithium diisopropyl amine LDA. This is just a hindered base. If you want to see its structure, it's an amine, so it's an N with 2 bulky isopropyl groups and the lithium here. So this will only deprotonate the least hindered position, giving you the kinetic enolate due to the steric bulk around here and here. So this will give you this enolate, OLI. There's your OR group, and then the next step of the reaction is just, and this would be done in one pot, we just add the LDA, and then when we quantitatively form the enolate, then we just add our second component, the 6-membered ring with the ketone, bond O, and then this would give you, that would collapse and that would attack here. So excuse the crazy arrows, hopefully it makes sense. And this will give us our carbon-carbon bond, forming this structure with alcohol here and double bond there. Or okay, and then the last step is just add acid and basically remove this as we discussed earlier. Okay, and that will give us the final product. So hopefully that clears that up, and this is a really typical example. We'll see these sort of connections, the alpha beta unsaturated and the aldol disconnection. We're going to see these come up over and over, and it's a really good strategy to use in larger retrosynthesis examples. Alright, that's it. Thanks for watching.